Okay, we talked about precipitation reactions. We're also going to talk about acid-base and gas evolution reactions. Two other classes of reactions, and these can happen in the same way, where we look at the ions coming in and we swap the partners and put them together in a different way and see what happens. In an acid-base reaction, which is also called a neutralization reaction, we've got an acid reacting with a base. They neutralize each other. Frequently, they produce water as one of the products. The equation that we just did with an ionic equation, that was an acid-base reaction. We can also have a gas evolution reaction. As the name suggests, a gas is evolved in this reaction, often seen as bubbling or fizzing. So we need to talk a little more about exactly what an acid is. We learned that an acid starts with H and that an acid forms hydrogen ions in solution. And that is the Arrhenius definition of an acid, produces hydrogen ions in aqueous solution. HCl is an example of this. It's a molecular compound, but when you put it in water, it ionizes and forms hydrogen ions and chloride ions. Let's think about what a hydrogen ion is. A hydrogen atom has how many protons and how many electrons? One of each, right? If it becomes a hydrogen ion, H+, it does that by losing one electron. How many electrons does it have left? None. What's left? It is just a proton. Okay, that's got to be crazy small, right? So it's a proton. I think of protons as being like newborn babies. Do you see little tiny babies just out and about by themselves? Walking down the sidewalk or even just laying on the sidewalk? No, they're too small to be out alone. That's how I think of the hydrogen ion. It's a proton. It's too small to be out alone. So when it separates from the chlorine here, it's not going to just be hanging out by itself. What it's going to do is it's going to ride piggyback on a water molecule. So it's going to ride on the water molecule, and so if you take H2O and you add an H plus to it, you get H3O plus. This is the hydronium ion. And this is what actually happens when you put an acid in water. Hydrogen ions are produced, but they're immediately picked up by the other water molecules. And so you get hydronium ions. So that's the truth right there. It's hydronium ions. Using H3O plus in all the equations sometimes makes things a little more complicated. And so a lot of times we'll refer to the hydrogen ion as just H plus. But we recognize that you never actually have H plus by itself. So we could talk about a baby, but we understand that somebody's there taking care of the baby. Because a hydrogen ion really is just a proton, we call acids, we use the protic as a prefix for acids. So polyprotic means many protons. So polyprotic acid can release more than one hydrogen ion. Sulfuric acid is a diprotic acid, meaning it can release two hydrogen ions. So if you've wondered why acetic acid is written this way, HC2H3O2, this is the ionizable hydrogen. Acetic acid is a monoprotic acid. It only releases one hydrogen ion. The ionizable hydrogens in an acid are always listed first. Sometimes there are other hydrogens, but they're not ever going to come off as ions. So that's why that happens. Just for full disclosure here, H2SO4 is a strong acid in its first ionizable hydrogen or ionizable proton, but weak in the second. What that means is that H2SO4, when it ionizes, it will make hydrogen ions and hydrogen sulfate ions. And it will go completely to this. And then this hydrogen ion can also come off, but it only comes off a very little bit.
So if you leave it long enough, it goes from one to the other? Or?
No, it will not go farther if you leave it longer. It comes to equilibrium. There will be a few sulfate ions, but it'll be mostly hydrogen sulfate ions. And you'll learn a lot more about that in Chem 1B. More than you would like to know, probably. So what is a base? The Arrhenius definition of a base is one that produces, substance that produces hydroxide ions in solution. So sodium hydroxide, soluble ionic compound, dissociates to form sodium ions and hydroxide ions. We can also have a base that does not have hydroxide in its formula. Bases like NH3. What NH3 does is it reacts with water and it will take a hydrogen ion from the water, forming ammonium ion and hydroxide ion. So when you dissolve ammonia in water, it produces hydroxide ions, but not the way you might expect, not the way these other bases do. Some bases produce more than one mole of hydroxide, so like barium hydroxide, BaOH2. When that dissociates, we get barium ions and 2 hydroxide ions. So you get 2 hydroxide ions for every 1 barium ion. That's the equivalent of a diprotic acid, except we don't have a fancy word for the bases that do that. So the hydrogen from the acid combines with the hydroxide from the base to make water. And this is not an ionic thing, but we can think of it that way. It doesn't hurt anything. If you think about putting H plus and OH minus together as an ionic compound, positive charge, negative charge, you just need one of each. You might say, well, it's HOH. And then you should say, that looks funny. Oh, wait a minute, that's H2O. So here we have our acid HCl. The hydrogen ion from that gets together with the hydroxide ion from the base and makes water. The other product is the other 2 ions. So we're doing that ion swapping thing again. The chlorine and the sodium are going to be together over here. We can write net ionic equations for acid-base reactions, and this is a typical net ionic equation. It's going to be H plus OH minus to give water. Occasionally it can be something else, but that's typical. Here we have an illustration of an acid-base reaction. So we've got hydrochloric acid, and we've got sodium hydroxide. And here the hydrogen ions are riding on the water molecules, and when they meet up with the hydroxide ions, they say, hey, I'm going to jump off of this hydronium ion, I'm going to jump onto the hydroxide ion, and then we'll all be water. Can you imagine the weird things that happen in my head, right? Sorry. So,
right. I know working with battery acid and pouring, what do you call it? Arm and Hammer, baking soda.
We will talk. Yeah, we will talk about that in just a minute. That's a gas evolution reaction. Very fun. So, anyway, that's what happens. And so now we don't see any hydrogen ions or hydroxide ions. They've been neutralized, turned into water. And all we've got is salty water. Some common acids and bases. There are 6 strong acids. You need to memorize those. So you memorize the 6 strong acids, and any other acid is a weak acid. These 3 are the binary acids of the halogens. HF is also a halogen, but that's the smallest sister, so she's weak. These are the strong ones. They're the bigger sisters. And then the other 3, I got nothing. Nitric, sulfuric, and perchloric. These are some common bases. Most of the bases we see are metal hydroxides. The only other one you need to be able to recognize as a base is ammonia. Ammonia is a weak base. So it forms, there's the equation down here, it does form hydroxide ions, but this reaction does not go to completion. it forms some hydroxide ions, but most of it remains as ammonia molecules. So writing equations. Write a molecular and a net ionic equation for the reaction that occurs between aqueous HBr and aqueous LiOH. So they gave us the formulas. So we've got HBr, and we're told that's aqueous, and we've got lithium hydroxide, also aqueous. To predict the products, we're going to separate these into ions and swap the partners. So HBr contains hydrogen ions and bromide ions when it ionizes. And lithium hydroxide has lithium ions and hydroxide ions. We're going to swap partners. And in an acid-base reaction, you're always going to get hydrogen and hydroxide. So over here, we'll have hydrogen and hydroxide together, and then the other two be lithium and bromide. And when we write these formulas, it's always the cation first and then the anion. It's like Mr. and Mrs. So H plus and OH minus, that's water. H2O, it's a liquid. It'd be silly to say it's aqueous because that would be water dissolved in water. And lithium bromide, the charges tell me I just need one of each, LiBr, and lithium compounds are always soluble from that list of solubility rules. Can't make a Q while I'm talking, so that one's going to be aqueous.
Why do you have the lines?
The lines, I'm showing that I'm putting these two together and these two together. The swapping partners. Yeah, so I took these two and they're here. Is the equation balanced? Yeah, it is. So I don't have to add any coefficients or anything. So that's the molecular equation. So we sometimes call that ME, molecular equation. It doesn't tell us that we have to write out the complete ionic equation, and so we can kind of just sketch it out and go directly to the net ionic equation. What I've done here actually is my sketch for the complete ionic equation. What I want to do here is I want to identify what is not actually present as ions. So this water is a liquid. So that is not separated into ions in the solution, and so I'm going to circle that to just kind of make a note to myself. That stays together. Soluble aqueous, soluble ionic compound, soluble ionic compound. This is an acid. We have to know, is it a strong acid or a weak acid? It's a strong acid. Strong acids ionize completely, and so this one will be separated into ions. So this is not ions, the rest of them are all ions. This is where the arrow is. Now I'm going to look for spectators, something that's the same on both sides. So I've got bromide here, and I've got bromide over there. Those are spectators. Or that is a spectator. And the other spectator is lithium. And so what I have left then is H plus hydroxide to form water.
So no matter how strong the acid is or base, it's going to always come out to that? Is that what you said?
Well, the net ionic equation is almost always going to come out to that. If you had a weak acid, it's a little bit different because then you have to include the weak acid molecule in your ionic equations. So it can be a little bit different. And so we would call this the net ionic equation. No, I wrote that in the wrong place. Down here, net ionic equation. Any questions? Let's do another one. So write the net ionic equation for the reaction between aqueous HCHO2, a weak acid, and aqueous NaOH.
It's not acetic.
It's not acetic acid. It's similar to acetic acid. It's a small organic acid. It's actually formic acid. So we've got HCHO2, and we've got sodium hydroxide. So I need to predict the products, and so this is an acid. It's a weak acid, but it does ionize, and so it makes these two ions. And this is an ion that we haven't looked at before, but we can do this even with acids we've never seen before. You take off whatever hydrogens are in the front, and the anion is just everything else. And then sodium hydroxide, we've got sodium and hydroxide. And then we're doing the same thing. We're just going to swap the partners. We're going to put the sodium with that weird thing and hydrogen with hydroxide. So we're going to end up with H2O from the H plus and the OH minus. And then we're going to get Na plus and CHO2 minus. I did not leave myself much room. So there, we just look at the charges, and we can write the formula for that, NaCHO2, and we can use solubility rules to predict the state. The first row says that sodium, lithium, potassium, and ammonium compounds are always soluble, no exceptions. So even though this is an anion we haven't seen before, we can still use the rule. This is aqueous. Yeah, it's soluble, and it does ionize. It just doesn't do that completely, but it will form ions. So when we're trying to write the net ionic equation, again, before I start crossing off spectators and end up crossing off everything, we have to identify what does not get broken into ions for the ionic equations. So anything that's a solid or a liquid or a gas. So water would be written as water. This is an acid, but it's a weak acid. So a weak acid is written as a molecule because that's what it mostly is in solution. So we're going to keep those two together. So the things that are as ions are sodium ions, hydroxide ions, sodium ions, and this formate ion. So I only have one spectator here. It's the sodium ion. So this is something I need to write as a molecule. So HCHO2, aqueous, plus the sodium ion was a spectator, so I'm leaving him out, plus hydroxide ion. And that's going to form water, and the sodium got crossed out, and this weird one, it's a formate ion.
So is it still going to be acidic solution, or is it still all the way?
This reaction will go to completion, and so whether the resulting solution is acidic or basic depends on the relative amount of the acid and the base that are present. But they will neutralize. And what will happen here is this will ionize a little bit, and this hydroxide will react with the hydrogen ions that have been produced. And so then there aren't any, and so then the acid will ionize more. And it will keep ionizing until all of its ions have been neutralized. And again, we'll learn a lot more about that in 1B. Yeah. Okay, Why is CHO2 not a spectator? Because this is a weak acid. And because it's a weak acid in an ionic formula, I need to write it as its molecular formula. Okay? And that's why. And so I circled it here to kind of alert myself, no, those stay together. Any other questions?
Water doesn't become a weak base on product side, and you have the reverse effect.
Yeah, we'll learn that water can act as an acid and it can act as a base, and it does so all the time. But for the purposes of writing ionic equations, we don't need to think about it. Yeah. Anybody else? We're going to do several titrations in lab this semester. And titration is a technique where we take a solution whose concentration we know and we react it with another solution where we don't know the concentration. And by measuring the volumes, we can figure out what the unknown concentration is. Stupid train. So, thank you. So, we add the one solution to the other until we get the stoichiometric ratio. So if it's 1 mole of this to 1 mole of that, we'll keep adding this second solution until we have equal moles of both. That's called the equivalence point, when they are equivalent to each other. And then we can calculate the unknown concentration using solution stoichiometry. So the big question is, how do we know when we've added just the right amount of stuff? Well, different types of reactions, we have to use different methods. For acids and bases, we can use an indicator that changes color depending on whether it's in an acidic solution or a basic solution. So at the equivalence point of an acid-base titration, the number of moles of hydrogen ions will equal the number of moles of hydroxide ions. We can do titrations with other kinds of reactions, but here we're just going to talk about acid-base reactions. So here we have illustrations and pictures. So here we've got, and we're just showing the hydroxide ions and the hydrogen ions because the other things are spectators. So here we've got a solution of a base in the burette, and we use the burette because it allows us to accurately and precisely measure the amount of liquid that has been added, and to do so in a very convenient way because we can control the stopcock and we can add a lot or we can add a little bit and we can control it, so that's good. Here we have our acid in the flask, and as we add the hydroxide ions neutralize the hydrogen ions. They combine to form water. When we get to the point where all of the hydrogen ions have been turned into water, then the indicator changes color. It's kind of cool. It's magic. I didn't mean to do this, but I'm wearing my phenolphthalein pink sweater today. So it'll turn pink, and that tells us, oh, you've added enough. You want to go to just barely turning pink, because if you keep adding it, it'll just get darker pink. But then you'll have we call that overshooting the end point, going past the end point. We would like the end point, which is where the color change occurs, to be at the equivalence point. Usually they're pretty close. So here we have this in pictures, our burette with sodium hydroxide in it, our flask here with hydrochloric acid. They both look like water. We're going to add the sodium hydroxide. As we are adding it and this acid begins to get neutralized, we'll start to see a little bit of pink color forming right where the sodium hydroxide is coming in. And we see it there because it hasn't mixed completely. So we stop the addition here and we give it a swirl and it mixes and the reaction continues and all the pink goes away. But the presence of the pink is telling us, okay, you're getting closer. The goal is to go from a clear solution, a colorless solution, to a pink solution in 1 drop or less. And that will tell you that we nailed it. That's too pink, but it shows up good in the picture. So let's do a calculation. The titration of a 20 ml sample of an H2SO4 solution of unknown concentration requires 22.87 milliliters of a 0.158 molar KOH solution to reach the equivalence point. What is the concentration of the unknown H2SO4 solution? Okay, so the temptation is great to use the dilution equation. M1V1 equals M2V2, right? Don't do it. This is not a dilution. This is a chemical reaction. How do I know? I've got two different substances here. I've got sulfuric acid and I have potassium hydroxide. There is no dilution where you can turn sulfuric acid into sodium hydroxide. So we can't use the dilution equation. This is stoichiometry. We need a balanced chemical equation. So we've got H2SO4. And for the purposes here, we don't have to write the state symbols, so I'm just going to leave them off. Plus KOH. So to predict the products, I'm going to swap the partners. So I'm going to put hydrogen ions with hydroxide ions, and that's going to give me water. And then I'm going to have sulfate ions and potassium ions. Now you may need to write all of this out, but some of you may be at a point where you can kind of see that in your head. Potassium ion and sulfate ion, okay, I need 2 potassium ions for every sulfate ion. K2SO4 is that formula. So I predicted my products, and now I need to balance the equation. Sulfate stayed together. I have a sulfate here, and I have a sulfate there. I have 2 potassiums, and here I only have 1. So I need to put a 2 in front of KOH. So now I've got 2 potassiums, and then I can look at the hydrogens. So there's 2 hydrogens here and 2 there, and over here I only have 2. I need 4. So I'll put a 2 in front of that. And this is where it gets a little confusing because I have oxygens from several different places. So it might make more sense to you to look at all of the oxygens. 4 oxygens and 2 oxygens, so a total of 6 oxygens over here, 4 and 2, 6 over there. Balanced chemical equation. I'm going to use this to organize my data, and I also need it because I need the mole ratio. It's a 1-to-2 ratio. And if you use the dilution equation, that will get lost and your answer will be off by a factor of 2. So sulfuric acid, I've got 20.0 milliliters, and I've got 22.87 milliliters of KOH, and I'm given the concentration of the KOH as 0.158. Remember that capital M means moles per liter. It does not mean moles. MOL is the abbreviation for mole. Capital M is moles per liter. And then I want the concentration of this one. Doesn't specifically say, but we want that in moles per liters as well. Yeah.
So after we balance, we're not even really using the right side anymore, right?
Correct. We don't need this at all for this problem. There are shortcuts that you can see once you get familiar with problems like this. This is a diprotic acid. It's got 2 hydrogen ions, and so that tells me that it's going to need 2 hydroxide molecules. And so I could do this without writing the equation, but I don't recommend it. Okay, so this is stoichiometry, and the path for stoichiometry was grams to moles to grams. And then sometimes we mix up the beginning or the end. So here we're going to be starting with the KOH because that's what we're given more information about. And this is the one with the question mark, so that's what we're going to. So we're figuring out stuff about the H2SO4, and we're starting with what we know about the KOH. We don't have a mass. We have a volume and a concentration. This concentration is the conversion factor. So we're going to start with this volume here. So we've got a volume, we've got milliliters. Now, in the Wednesday class, we did this problem where we converted milliliters into liters and did the problem that way. So you can watch the video and see that. I'm going to use millimoles today. So if we're going to do millimoles, we'll have millimoles. We've got milliliters, and so we're going to make this millimoles and millimoles. And then at the end, we're not actually going to grams. So what we're going to do is we're going to stop here with millimoles. And if we take millimoles and divide by milliliters, the millis cancel out and we get moles per liter. So that's the plan. So I've got 22.87 milliliters of KOH. And this concentration, moles per liter, I can make that millimoles per milliliter. Because I'm multiplying the top by 10 to the minus 3, and I'm multiplying the bottom by 10 to the minus 3. I've made it look different, but it's actually the same thing. So 0.158 millimoles of KOH, and milliliter is in the denominator. Then I'm going to convert to millimoles of the sulfuric acid, dividing by millimoles of KOH. A millimole ratio is the same as the mole ratio, 1 H2SO4 for every 2 KOHs. So 1 to 2. I'm going to stop the calculation there. 22.87 times 0.158 divided by 2. 1.80673 millimoles. We should always keep track of our significant figures. The volume had 4, but our molarity only had 3. So this has 3 sig figs. Millimoles of sulfuric acid. To get the concentration, molarity is moles per liter, or millimoles per milliliter. So I'm going to take the moles that I figured, 1.80673 millimoles, and I'm going to divide by the volume of sulfuric acid that was used, 20.0 milliliters. So I divide by 20, and the number is 0.90336. So I'm going to round that to 3 sig figs. Nope, I screwed up. It's 0.903. Well, zeros are important. 0.0903 millimoles per milliliter. But to get molarity, all I do is cancel out the millis. Any questions?
When can't we do that thing that you do with milliliters?
When can't you do it?
Yeah, like, because if we're converting stuff and we just add the M.
Well, the thing is, you can do it to any molarity. So you add the M here and the M there. You can't take a volume in liters and just stick a milli in front of it. You can't take a number of moles and just stick a milli in front of it. The reason we can do this is because we're doing it on the top and the bottom. And it's the same as multiplying the top and bottom by the same number.
Oh,
Okay.
You should make it micromoles.
Yeah, we could do micromoles or megamoles or anything we want.
But at the beginning, if we changed 20.0 milliliters and 22.87 milliliters to liters and that started, we still work out the same, right?
You'll get the same result. So what he's asking is, well, couldn't we just convert this to liters and then it'll end up the same? Well, we can convert this to liters. We also have to convert this to liters. And so this number will be smaller and this number will be smaller, and we'll get the same answer. And which method you use, you should use the one that makes more sense to you. Okay? I see a lot of craziness when students convert milliliters to liters. So I talked to the other class about this. I'll talk to you about this as well. So obviously you can do the whole writing it out thing, milliliters on the bottom, liters on the top, and here's the 10 to the minus 3. Like, it's a little tedious. Milliliters to liters, it's always just moving the decimal point 3 places. The trick is, which direction are you moving it? Well, you move it to the left in one conversion and to the right in the other conversion. So this 22.87 is going to be 0.02287 liters. Converting this to milliliters, I'm going to move the decimal point to the right.
After we find a balanced chemical equation, can we use the formula?
What formula?
The
M1V1? No, you can't. You can't use M1V1 because you've got moles of H2SO4 on one side and moles of KOH on the other side, and those don't cancel out. Because you'll lose this one right here. You'll lose that. Now, can you do that and compensate for that? Yeah, but that's asking for trouble. That's really asking for trouble. Because you have to then figure out, do I divide by 2 or multiply by 2? And yeah, if you just do it this way, it always works. So when you're converting milliliters to liters, turn your brain on and think about it. How big is a liter? Well, it's half of a 2-liter soda bottle, right? So you got a picture of that. It's kind of big, right? How big is a milliliter? Imagine those little 10 ml graduated cylinders. A milliliter is about that tall in there. Little tiny thing, right? So if I take 22 of these little guys, that's going to make a smaller amount of the liters. Because what I sometimes see is that students tell me, well, it's 22,870 liters. That's 11,000 soda bottles. Right? That's backwards. Okay? So, put your thinking cap on and use a little common sense, and then you can convert back and forth between milliliters and liters very easily. You're moving the decimal point 3 places. Liter is the big unit. It has the small number. Milliliter is the small unit. It has the big number. Okay? So whether you want to use millimoles or you want to just, convert to liters is really up to you. The millimole concept comes in handy in certain types of experiment calculations because the numbers that we get are so much nicer, right? We got 1.8 instead of 0.0018. It's just a lot less zeros. Okay, I took too much time on that one. Okay. Gas evolution reactions. We can have a gas that is formed directly from exchanging ions. So here we've got K2S and H2SO4. If we swap the ions, we get potassium with sulfate. So there's our K2SO4. And we've got the hydrogen ions with the sulfide ion, H2S. This is a gas, and we know it's a gas because I just told you that it's a gas. So now you have to remember, H2S is a gas. It smells really bad. Most compounds with sulfur in them do not smell good. The other way we can have a gas form is we can form something that is unstable. So here we've got sodium bicarbonate or sodium hydrogen carbonate. This is baking soda. So this is the reaction that Jeremy was talking about. Sodium hydrogen carbonate and hydrochloric acid. So we put the chloride with the sodium and we get sodium chloride. We put the hydrogen carbonate with the hydrogen and we get H2CO3, which is carbonic acid. Carbonic acid is not stable. It decomposes. And that's something you just have to remember. It decomposes into water and carbon dioxide. And this is where all the bubbling and the fizzing come from. Similar thing will happen if you take some vinegar and you put some baking soda in it. It'll fizz. That gas is carbon dioxide.
So can you work with, are you able to work with the liquid carbonic acid? Or how do you?
That's a good question. How do you work with carbonic acid? Well, the only way to have a high concentration of carbonic acid is to have it in a pressurized container. And that's actually what's happening in a can of soda. Carbonic acid is used to carbonate soda. And so the bottle or the can has to be airtight, and it's pressurized, and there's a high pressure of carbon dioxide gas above the liquid. And that keeps the carbonic acid in solution. As soon as you open it and it goes psst, and lets the pressure out, you see the bubbles start to form, and the carbonic acid is decomposing and the carbon dioxide is coming out of solution.
So carbonic isn't one of the strong acids?
It is not a strong acid, no.
Okay, I was thinking it was.
No, not a strong acid.
That would not feel strong acid.
So here are 4 different types of gas evolution reactions that could show up on an exam. And what we're really interested in is these guys here and this one. So if you do the partner swapping the partners and you get H2S, remember that that's a gas and just write the state symbol G. If you swap the partners and you get carbonic acid or sulfurous acid or ammonium hydroxide, these are unstable. They will produce these gases, and it's actually a nice pattern here. So I'll show you how this pattern works. So H2CO3. All of these decompose to form water and what's left. Okay, so if we remove an H2O from this formula, well, so I'm going to take off both of the hydrogens, and I'm going to get rid of one of the oxygens, so then I'll have 2 oxygens left. So I got H2O and CO2. See that? I can do the same thing with sulfurous acid and with ammonium hydroxide. H2SO3, that's going to decompose to form water, and got to get rid of 2 hydrogens from the formula and get rid of 1 oxygen, SO2. SO2 is a gas. Just have to remember that. So CO2 is a gas, SO2 is a gas. Ammonium hydroxide, same thing. It's going to decompose to form a water molecule, and we can figure out the formula by just getting rid of 2 H's and an O from ammonium hydroxide. So let's get rid of this H, and there's the O, and I need to get rid of 1 other hydrogen. And so I'm left with NH3, which is a gas. Okay? You can pass the class without remembering these guys. Okay? But if you want an A, you should remember these guys. So write a molecular equation for the gas evolution reaction that occurs when you mix aqueous hydrobromic acid and aqueous potassium sulfite. So we've been given names, so we need to write the formulas. Hydrobromic acid, that's a binary acid. So it's hydrogen ion and bromide ion is what it forms, so that's HBr. And potassium sulfite is potassium ion and sulfite ion. So that'll be K2SO3 aqueous.
I have a question.
Uh-huh.
On the last slide for the, that creates the NH3,
Mhm.
what does it also create?
Water.
Just water? Okay.
Yeah, they all basically, when they decompose into water and what's left. So to predict the products, we're going to swap partners. So I'm going to have potassium with bromide. So that's going to be KBr. And I go through the solubility rules in my head. Potassium ion, those substances are always soluble. And then I've got H plus with SO3 2 minus. So when I put those together, I get H2SO3. That's one of those unstable ones. So what does it do? Well, H2SO3 decomposes to form water, and what's left after I remove 2 hydrogens and an oxygen from this molecule? SO2. So up here, instead of writing H2SO3, I figured out separately what it decomposes into. It decomposes into water and SO2 gas. And then I have to balance it. Sometimes it's easiest to look for something that's not balanced. I'm looking here at the K2 and there's K. So I need 2 potassiums over here, and that gives me 2 bromines, so I'll go over here and fix bromine. And so I've got 2 hydrogens, and I go over here and I've got 2 hydrogens. I've got 1 sulfur and 1 sulfur, 3 oxygens, 1 plus 2, 3 oxygens. So this is an example of a reaction where a polyatomic ion does not remain intact. The sulfite ion, when it combined with hydrogen, this was unstable, and so I don't have sulfite anymore. It came apart. Any questions?